This video is a key to the Learning Objective 7 practice problems. Learning Objective 7 is nucleophilic aromatic substitution, and there's two mechanisms that we know. One is SNAR, one is benzene. If you notice on this reaction, we have sodium hydroxide. That can be a nucleophile or a base. If it was a nucleophile and it attacked the fluorine on one of the rings or the chlorine on the other ring, that would allow us to have a substitution on an individual ring. That would not allow us to make a molecule that is big, like this one that has both of these molecules put together. Notice that the molecule, the starting material on the right, is the bottom portion of the big molecule in the product, except the fluorine that was on the starting material on the right, the purple circled one. The fluorine's gone and it has been replaced with an oxygen. So this purple circled starting material is going to be attacked by a nucleophile, but not the normal hydroxide nucleophile. What happens is hydroxide reacts with the OH group on the other starting material and deprotonates it to make a phenoxide, which is actually a nucleophile. So the phenoxide nucleophile attacks the carbon where the fluoride leaving group is and gives us an intermediate. It's a big old gigantic intermediate because it has both of these aromatic rings and all their substituents there. Otherwise, this looks like the intermediates that we saw when we did the reaction mechanisms with the nitro groups on it. So that's our intermediate. Now that we have that intermediate, the second step of the mechanism is really pretty easy. The pi bond reforms and the fluoride leaves, and it gives us this bigger product with the two aromatic rings bonded together using an oxygen bridge that was already attached to one of the rings. Okay, next problem. Treatment of p-bromotoluene with sodium hydroxide at 300 degrees Celsius produces a mixture of two products. In contrast, treatment of n-bromotoluene with sodium hydroxide at a similar temperature produces a mixture of three products. All right, 300 degrees C is really hot. And we're getting mixtures of products. That should make us think of the benzene mechanism because we can get mixtures of products with the benzene mechanism. But in class, I told you that the only way that could happen was if the base was amide, which is a stronger base than sodium hydroxide. Apparently, if you use sodium hydroxide, you can get the reaction to happen, but it has to have a much higher temperature. Here is the overall reaction that was described in the sentences of the question, at least the overall reaction for the p-bromotoluene. Now we'll walk through the mechanism. In the first step, the hydroxide deprotonates the position next to where the bromine leaving group is, and that gives us benzene. And then the benzene reacts with hydroxide to, it's a nucleophile, it adds to one of the carbons in the triple bond and generates an anion. We can't have anions as products, so that deprotonates the solvent to give us the meta-bromotoluene. Our mechanism needs to also explain how the para-bromotoluene is formed. So I have another copy of the benzene intermediate, and it's going to react with hydroxide and have an attack happen at the other position. So again, we get the anion that abstracts a proton from the water solvent and gives us the product p-methylphenol. All right, But now we need to explain the other half of the question, which is about N-bromotoluene and how it gives 3 different products. So I have that on the next screen. The overall reaction is shown here. We need to explain how all 3 of these form. It's going to basically be the same thing. The hydroxide deprotonates the toluene structure at the carbon next to bromine to give us the benzene. And then the hydroxide adds to the benzene at one of the carbons to make an anion that gets protonated. This can also happen on the other side. And when it happens on the other side, we get the para product after it's protonated. And then I am going to show you the other place that we could have had deprotonation was on the carbon between the bromine and the methyl. And that gives us 2 different products. So we will have 25% ortho product, 25% para product, and 50% meta product, because the meta product is formed from both of the 2 pathways that could take place. Okay, next question. The zwitterion shown below decomposes when heated to yield nitrogen gas, carbon dioxide, and another substance that's too reactive to isolate. When the compound is heated in the presence of furan, the product shown below is obtained. What is the intermediate that forms? Propose a mechanism to explain this reaction. Notice that the nitrogen comes from the N2 that's attached at the bottom right of the structure and circled in purple. The carbon dioxide comes from the top right of the structure and boxed in red. And the other part of the structure is where we get benzene, and the benzene reacts with furan to make this Diels-Alder product. So now I'm going to show you the arrow pushing mechanism, and I drew a new copy of the molecule to put my new arrows on. So I have the carboxylate at the top and the diazonium at the bottom. The carboxylate, the O- makes a double bond to make CO2, and the electrons that attach to that carbon to the ring go to make the benzene, the triple bond. And that encourages the diazonium to leave as nitrogen. This gives us the benzene, and it gives us CO2 and N2. Benzene will react with furan. Benzene is the dienophile, furan is the diene, to give us this Diels-Alder adduct. Okay, the last one on Learning Objective 7 practice. We have a complicated structure with chloride, which is a good leaving group. I have sodium methoxide, which is a base, and it's also a nucleophile. Notice that the nucleophile came in at the position where the leaving group left from, so this is probably the simpler kind of mechanism rather than the weird benzene mechanism. So the methoxide base nucleophile attacks the carbon with the chlorine and makes an intermediate that has resonance structures, and I have arrows to show how these different resonance structures can turn into the other resonance structures. And there's a bunch of them. I kept going on the resonance structures until I got to one that's a really good one with the negative charge out on the oxygen outside of the ring. And now I will show the final step, which involves the double bond, the negative charge on the oxygen going back to form a double bond, and all the electrons reorganizing so that chloride can leave. We could have drawn the blue arrows on any one of the structures instead of starting on that last one that we had. I just did it on that one because it didn't already have a bunch of arrows on it.